Walk onto any American machine shop floor and ask about AI-generated 3D models, and you will hear the same dismissal. It generates toys, assets for video games or 3D printing hobbies, but nothing with the rigor for industrial manufacturing. That skepticism was grounded in technical reality. For years, the foundational output of generative AI was the polygonal mesh, a data structure composed entirely of triangles that approximate a surface. These meshes are functionally useless for precision manufacturing. They lack parametric editability, contain no feature histories, and cannot be imported into CNC machining or injection molding simulations without error-prone conversions. Engineering relies on exact, continuous mathematical definitions. This standard has governed digital modeling for decades. Mechanical design requires boundary representation, or BREP. These models define physical objects through precise analytical surfaces and curves, ensuring a solid is perfectly watertight and manifold. This is the format behind every production-ready STEP or SLDPRT file. This diagram shows a standard mesh gear on the left, built from jagged triangles. On the right, the BREP gear utilizes smooth, mathematically defined analytical surfaces. As of 2026, the technology has reached a turning point. AI can now natively synthesize this deterministic BREP geometry. Generative models have transitioned beyond aesthetic pixel approximation. These architectural breakthroughs allow neural networks to function as deterministic engineering engines. To produce a mechanically valid BREP, an algorithm must adhere to strict topological rules. Every edge must have precisely 2 incident faces to ensure the solid is watertight. This created a compatibility paradox for deep learning. Neural networks excel at continuous parameters, but they historically struggled to merge that probability with the rigid, discrete rules of solid geometry. One major architectural solution involves explicit graph representation. This animation shows how a 3D model translates into an undirected graph. Physical surfaces are mapped as nodes, while topological connections become bridging edges. By utilizing an adjacency matrix, the model generates only geometrically meaningful surface connections, reducing redundant computational costs during inference. A secondary approach utilizes hierarchical diffusion, generating the solid from a root node down to individual vertices. This top-down denoising allows the AI to synthesize doubly curved analytical surfaces that were once impossible for generative tools to create. By forcing neural networks to operate within discrete graph topology, developers have successfully reverse-engineered the exact mathematical format required for physical machining. These capabilities are now being applied to the most requested feature in legacy manufacturing: the ability to feed a flat blueprint into a system and instantly receive a parameterized 3D model. In practice, one-click geometric reconstruction frequently fails due to multi-view orthographic blind spots. AI models struggle to reconcile front, side, and section views into a single, unified 3D topology. Typical failure modes include misinterpreting internal features. Computer vision systems frequently confuse internal fluid channels or section hatching for external physical protrusions. Semantic engineering extraction provides immediate utility for legacy prints, where geometric reconstruction remains inconsistent. Traditional optical character recognition fails on complex prints because it cannot parse multidirectional text or dimension lines that intersect with characters. Modern architectures bypass standard OCR by recognizing the structural context of the drawing, allowing the system to identify semantic feature control frames. On this scanned blueprint, drawing lines fade out while geometric dimensioning and tolerancing data is extracted. Symbols for flatness and position are structured into a JSON tree. The AI normalizes ambiguous legacy dimensions, ensuring various notations for an identical chamfer output exactly the same. This extracted data feeds directly into enterprise resource planning systems. This allows automated feasibility analysis and real-time supplier quoting without the risk of manual transcription errors. Liberating semantic manufacturing information from flat files provides far more immediate economic value than simply generating a standalone 3D shape. Since direct 2D vision has limitations, the industry has turned to a more reliable method for creating new 3D parts from scratch. Programmatic generation uses large language models to write domain-specific parametric CAD code rather than predicting new 3D geometry from pixels. This method offloads the burden of mathematical exactness. The probabilistic AI handles the logic, while a deterministic geometry engine compiles the final shape. A natural language prompt for a hexagonal gear translates into CAD query code. If the code contains a topological impossibility, the compiler flags the error. The AI agent reasons about the traceback error and rewrites the script until the solid geometry compiles successfully. This architecture is a generate, simulate, refine closed loop. It allows the system to autonomously identify and correct errors in 3D construction that would baffle a standard visual generator. These loops use datasets like 0-CAD and hist-CAD, which contain millions of constraint-aware construction sequences. LLMs fine-tuned on these specialized datasets have reached a 100% valid syntax compilation rate for generated CAD sequences. By outputting editable code, these systems ensure the engineer retains total parametric control, transforming the AI into a high-speed, hyper-accurate macro generator. A valid BREP model defines the shape, but engineering requires validating that geometry against physical forces like thermodynamics and structural integrity. Traditionally, validating a design through finite element analysis required hours or even days of slow, algorithmic batch processing. Deep physics models have bypassed this bottleneck. These are foundation models trained on tens of millions of 3D shapes and their physics performance data, replacing traditional solvers with instant AI inference. A live parametric model where a slider reduces an aerospace bracket's thickness. The AI instantly predicts shifts in the stress distribution. This immediate feedback allows engineers to evaluate thousands of design variants and the time it previously took to evaluate one. Physics-informed AI drives generative design for additive manufacturing. Algorithms iteratively grow material only along necessary load paths, creating shapes satisfying specific stress fields. The results are organic, multi-scale lattice structures. These biomorphic forms are lighter and stronger than conventional solutions, pushing the limits of fuel efficiency and payload capacity. Integrating real-time physical inference elevates generative AI from a drafting tool into a high-speed optimization engine. The final constraint on these systems is physical safety and legal liability. In regulated sectors like aerospace, the stakes of a structural failure are extreme. An artificial intelligence cannot hold a professional engineering license, nor can it absorb the legal liability if a mechanical component fails in flight. To address this, organizations utilize a simulation workbench safeguard. AI explores the design space at high speed, but the final model must still pass through a certified deterministic solver for validation. AI is also acting as an auditor, scanning multi-page drawings to ensure standards compliance and metrology readiness before production begins. As automation handles bulk 2D drafting and layer cleanup, the workforce is shifting. Demand for rote drafting is shrinking, while the need for CAD auditors and automation engineers is surging. These systems only generate ROI when they are deeply integrated into existing product lifecycle networks, which still require human oversight to manage and verify. In 2026, AI serves as a cognitive exoskeleton, automating drafting tasks, shifting mechanical engineering from basic geometry building toward complex systems architecture.